Hello, physical science students. Mrs. Dobson speaking. So I just wanted to catch up with you guys on Kepler's laws, talking about the key document you guys got today to review over the 3 laws, and the third law practice, kind of making sure you know how to do that on there. Okay. Now, first thing is with the lab. So with the lab, you are supposed to be done with. You had it assigned last week. I assigned it in chunks. We did the first law, the background pre-lab questions, and through the first law. You had to have extra time on Friday to finish because my videos wouldn't load until later in the day. So you were supposed to finish that on Friday. I did the demo. That's what these two are. I did the demo of going through the lab with the 2 videos here, and then I also made a PowerPoint to add the document of the data on. So as far as the lab goes, let's open this real quick to review this of where you should be at with it. Let's see if it loads here. I have to turn that off. All right, so you should have already had the pre-lab questions done. And I've only had 1 student turn this in, so I'm worried about if anybody's participating right now. Oh, this is being really slow. Okay, so you're supposed to make your prediction. I've already talked about this in that video, so I don't want to review all this, but you're supposed to have your prediction here, and it's up to you if you made your own. And then I did in the demo, I explained and showed you how to do that, and you can just use my information, like I've said before. And then keep going here. It's kind of slow here. Calculating eccentricity, I gave you the values, so you just had to do that. Use the data table, you're supposed to explain. Hypothesis supported or refuted, that was supposed to be done through Friday. And then Monday, you were supposed to finish this up. And if you need to finish this today, make sure you do that. You click on the link. Make sure you click on the W player to run. And looking at the second law and answering a few questions. And then third law, same thing. You're just looking at the interactive and then just really reading through this sample problem, because that's the things that we're going to go through today is the third law focus on how to do that. Okay. And so we'll probably go through Mercury together. All right. So that's for the lab, that you're supposed to be through that part. You could just be through that page. You don't have to do anything else right now. I might assign more of it later or whatever, but you didn't have to complete anything but through page 4. All right, so let's go to this key here and let's review the 3 laws. Normally in the classroom, I would have this projected on the screen and we'd kind of talk about the 3 laws and we'd review over them. You had your vocab you should be reviewing over. You should have your list done. I don't remember how many people turned those in, but it was not very many. We have a class of 23, and I'd have to look later to see how many people actually turned that in. So it's very important to learn this information as far as the standard that you're supposed to cover about Kepler's laws of motion, okay? So through analyzing Tycho Brahe's observational data, because Kepler was his apprentice, he used his data, his previous person before him used his data, was able to explain the motion of planets in our universe through 3 laws. So the first law that you should have seen was where we created the ellipses. In 1609, the first law is known as the law of orbits or ellipses. So just keep that in mind. Maybe if you remember that basic thing, like I usually say the law of ellipses, or orbits, whichever is easier for you to think of. Okay, I visualize an ellipse that's like an egg-type shape, kind of oval in my head of what was drawn, like on the lab that we did. We had 3 different ellipses that we created. So that elliptical path represents the planet's orbit around the sun. Remember, the sun is at one of those focal points. You got 2 dots, 2 centers of an ellipse. One of those centers is the sun. Okay, and so this first page shows you the explanation or the law, the basic part of the law. You can see more of that on the lab where it goes through each law and explains that. On here, it just gives you a brief overview. And the second page of this, so I'll kind of go back and forth, is the drawing or description, like a visual representation of the law. Okay, and the ones you did on the lab are the same type of thing. So this is the technical definition. The orbital planet is an ellipse where one focus of the ellipse is the sun. So planets go on an elliptical path around the sun. One of those focal points is the sun. So let's go ahead and skip those for now and come to this one here. So here we see Normally on your paper, this would be blank. This is just the key that we use for when we go over it as a class. So you would have a blank paper in front of you and fill this out, but I figured you guys could have this as a resource. So you would draw and label each part of the ellipse. So you draw an ellipse, whether you use the actual tool of using the push pins and the string and all that, you could do that, or you could just make kind of an oval type shape. All right, so parts of the ellipse that you need to include the two foci within the ellipse, labeling one of them the sun. So you at least need to have your two dots. So you can draw it like this, two dots. One of those is the sun, maybe you make it look like the sun, and then you have your elliptical path around that. You don't really need anything else besides the sun. So the two focal points, the sun is one of those. You got the elliptical path, and on the elliptical path is a planet. Okay, it's really just planet, sun, your other focal point, and then the path there. You do not need aphelion, perihelion, that's going to come up in the next one. And you do not need the minor and major axes, but you can if you want to. So really just planet, sun, two focal points, and then your ellipse. That's all you need to create your ellipse or to represent an ellipse, okay? So that's the first law. The planet goes around on this elliptical path around the sun, okay? And the second law, we'll talk more about what happens as the planet goes around the sun, okay? So I don't know if there's any questions on the first law. I haven't heard much response from people. I've only had a few people turn things in at a time. All right, so the second law then here, in 1609, so same year, the second law of planetary motion was known as the law of areas, okay? So areas, I think of amount of space that something takes up. A line from the planet to the sun, okay? So from the planet where it's on its elliptical path to whichever focal point is the sun, sweeps out equal areas and equal amounts of time. So equal areas, equal amount of time, okay? So on that one, let me scroll down and show you the visual, and then maybe I'll even go to the interactive and show you that too. It might help you with that part. So you would draw some type of elliptical path. This is sun. We can still have our other focal point over here. So in this example, the sun is on this side, and then we have another invisible focal point that's there as the other center of the ellipse. So this little blue dots, that would be your planets. You can label that the planet. See, so the planet blue dots, the sun is the black dot, so you could label that if you wanted to. And then it's just showing as it goes around, it's just connecting, like it said, equal line, line from the planet to the sun. So that's what those are. And then it's showing that the amount of space is equal areas, equal time. So we'll talk about that too. It looks a little different, like if it's comparing these two, they look a little different, but there's something that happens as it gets closer to the sun. So then a perihelion, which I would label this vocab term. This right here would normally be labeled on this side because the planet is closest to the sun at this point. So that would be its perihelion to the sun. It's closest to the sun and moves fastest at that point. Aphelion is when it's furthest away from the sun, it moves slowest. Okay, so somewhere over here, it's farther away or farthest away, and so you'd label aphelion, farthest away, moves the slowest. So as the planet's going around, it kind of speeds up as it gets close to the sun and then kind of slows down a little bit, slows down and speeds back up as it gets closer. So this actually ends up being the same because it's going so fast, it ends up being equal areas in the equal amount of time, even though it looks a little different. Okay, so that is Kepler's second law. So we can look at the interactive if you haven't already done so on the lab. That's why I wanted you to do that ahead of time so you can understand it. Let's see if this loads here. Just in case if you have not loaded it here. Okay, I might have to manage this for the flash was blocked. So I'm going to manage and ask first. Okay, so let's see if that works now. Let's refresh it. Okay. Click to enable. So that's how you fix that if that happens to your Chromebook too. Maybe that's the issue of why some people haven't done them. So here we go. Let's see. We'll go to the Earth right now. So as it's going around, you can pay attention to the area swept out over here, 8,700. Okay. So as it goes differently, you see 8,700. So you can kind of keep looking. It's the same amount of area that's swept out. And this one, the eccentricity is 0.02. So remember, if it's closer to 0, that is more of almost a perfect circle. And as it gets closer to 1, it's more eccentric or more flat. Okay, so it might be hard to tell in this one when it's moving faster, but whenever it's closest to the sun is when it's going to move faster. I don't think on this one it shows the speed on this one. Okay, so if we go to, so that's Earth, if we go to Venus, it's about the same. It's actually eccentricity is right at 0, so it's actually a perfect circle. You can see it's swept out equal areas, equal time as it goes around. Okay. So this is what you're supposed to look at to see what happens. We go to Mars, because we should have started Venus. Venus is second from the sun, then the Earth, and then Mars is next in its orbit as far as our solar system. So Mars looks a little bit more different. It's 0.1, so it's a little bit more eccentric. So you can watch as it gets closer to the sun what happens. I don't know if you can tell right now. It goes a little bit quicker, and then it will kind of slow down a little bit. So as it gets on this left side here, it's going to be quicker than it is over here. Just watch the speed of that. The area is still equal, but it's slower on that side. Okay, Jupiter is even farther away, 0.05 eccentricity. Oh, not a very high eccentricity. Okay, it takes a lot longer to go around though. And then the other two we have, we'll go to Pluto first because it's a dwarf planet, used to be considered a planet in our solar system, and then we'll go to the comet. You can really tell more of a difference with those compared to some of the other ones. All right, so you can see still arrows, equal time. Pluto, 0.25, so that's quite a bit higher than the other ones. So you can see how eccentric it is, and watch as it gets close to the sun, what's going to happen. It's moving a lot quicker, and that's going to slow down as it moves away. Do you see that difference? See, Pluto and the comet are really easy to see that. Okay, let's watch it one more time, and then we'll look at the comet and see how eccentric that one is. So equal areas, equal time. It just looks a little different as it goes around, and look at it speed up. Zoom. Why does that happen? So that's what we need to think about. Why does that happen? It connects a little bit to our next unit that we'll be doing on gravitational force. So think about that. All right, let's go to the comet. Look at this one, guys. 0.8 eccentricity, very close to being the highest eccentricity, which is 1. It just zooms around the sun as it gets close. So very elliptical path, right? Still equal areas, equal time, and here it goes. It's going to go a lot quicker. It's going quicker. Here we go. Shoom. And it goes around slower as it gets away. Okay, so that's what you're supposed to look at on your laws here, and then you're supposed to answer these questions here, which might help you more from what we went through. So there's kind of that visual. Go back here. So we got the law of ellipses so far and law of areas. I don't know if there's any questions on the second law. Let me know. Email me with any questions you have on knowing that. So knowing the terms perihelion and aphelion is very important there, when it moves faster and slower. This is just the basic elliptical path. This moves faster or slower based on perihelion and aphelion. Distance from where it's at in relation to the sun and its orbit. All right, later on in 1616, the third law of planetary motion is known as the law of periods or harmonies. Okay, so usually call it the law of periods because it has to do with the vocab term that we've had, and it relates the mathematical equation. So the period of a planet's orbit. Now, if you looked up the definition for period, there's a lot of different definitions depending on what you're talking about. If you're talking about astronomy, though, we're talking about the time it takes for the planet to go around the sun. So that value, whatever that is, the time it takes to go around the sun is squared. Okay, and we'll talk more about what squared means if you're not sure what that means. It's to the second power. It's proportional or directly proportional to what we said before, or related to its average distance from the sun cubed. So the period is related to the average distance from the sun. The period of time it takes to go around the sun is related to the distance from the sun. Squared for period, cubed for the sun. Okay, so keep that in mind. Cubed means to the third power. And directly proportional, remember, means that if the time it takes to go around the sun goes up, what do you think is going to happen to the distance it is from the sun? If it's directly proportional, they should both go up. If one is less, then the other is less. Okay, that's what that vocab term means. All right, so let's go down and look at the visual here on our key that I sent to you guys. So third law of planetary motion. You had this on your lab. Right here, it kind of explained it right here and gave you the variables and gave you a sample problem. I also have a sample problem on the key. I'll have to look at the diagram here in a second. All right, from the interactive, close this interactive now. Go ahead and click on this so it's ready to go. So that goes right to it. Okay. All right, So write down the third law of planetary motion. So here's our equation. So normally you'd write this equation down in class. It's cubed, or it's squared and then cubed. P represents the period, or the time it takes to go around the sun, measured in Earth years. And then A represents the distance a planet is from the sun. It's measured in AU, or astronomical unit, which we'll be doing a scientific notation thing coming up on probably Monday that relates different types of distances from the sun as in comparison to the Earth. Okay, so let's look at this visual here. This is from your lab, your interactive. It does give the example here, trying to find the revolution of how long it takes to go around the sun based on distance from the sun. So we already kind of talked about this, but let's just go ahead and plot Venus. So we're going to look at Venus, and it's going to go, you can see it gives you this information here, how far away it is, the eccentricity, the mass of it. So you can see how quick that was. Okay, and it made the dot on the graph relating the time it takes to the distance. Okay, let's go and click on Earth and hit go. Okay, and again, look, it's farther away from the sun. What happens to the time it takes? It takes a little longer. We can always, I don't know if we can pause on here. Okay, let's go to Mars. It's a little farther away. You can look at the values over here. A little bit farther away, right? So the time it takes is more. And you can see that path is going straight up. Right, Jupiter's next. It's farther away. I need to maybe zoom out too so I can see. So let's look closer, but you can see how big that path is. I guess it's good. You can see it going all the way around. Right? How many years it takes. Look how many years it takes compared to the other one. So it's farther away. So look at that big difference there. There's a big gap, but it's still going way up, right? From Mars and Jupiter, that is a big difference. All right, we also have asteroid Ida. So we can see how an asteroid moves as far as the path and the eccentricity and all that. It gives it there. Okay. And you can customize your planet if you want. So you can definitely see as the distance goes up, the time it takes to goes up. So they're directly related to that straight path there. Okay. You can always pause when you're looking at this video too if you need to. All right. So isn't that cool? How that's a direct relationship. All right, so on the key, that's what we talk about. With that equation that the Kepler came up with, he found that there's a direct relationship between a planet's orbital period or time it goes around the sun compared to its distance. So in other words, the further something is or more distance between a planet is from the sun, then the period or the time it takes to go around is more. To go around once or in general, it will take more time if it's farther away. As compared to a planet that is closer, okay, which means it has less distance between itself and the sun, then the period will be shorter or have less time. So farther away, more distance, I'd have my thumb going up. The period is longer, so my other thumb's going up. So they're both going up. Therefore, it's directly related. Same thing with the other one. Decreasing the distance, my thumb is going down. The period, that decreases, so that's going down too. So both going up or both going down. Therefore, it's a direct relationship. All right. So then for the example of how to use the math, you can use the math looking at this here. Let's look at this problem first from your equation here, from your lab. Planet X has an average distance from the sun of 1.76 AU, or astronomical unit. What is the planet's period of revolution in Earth years? So in other words, we're trying to figure out the time it takes to go around. First thing to do is write down the equation, okay? Next thing we're going to do is we're given the distance, so we're going to plug in our distance value. Now, on these, I would have AU in our parentheses, and I'll show that on the assignment page in a second here. So we take that, we cube it, which means pretty much 1.76 times 1.76 times 1.76. If you don't have a calculator that can cube something, you can always do that, okay? And then you just have to get rid of something that's squared. The opposite of squaring something is square rooting it. So you square root that 5.45 AU, and you get 2.33 Earth years for this planet. It takes them that long. If they're that far 1.76 AU away, it's going to take 2.33 Earth years to revolve around there, around the sun. Okay, so here's the example on the key, example problem here. If the given distance away from the sun is 5 AU, so that's our distance or our A, what would be the astronomical object's period to orbit the sun, or how long would it take to go around the sun? So we don't know P. In all the situations that we do for your class, we're always solving for P or time, and we are plugging in our value for distance. Now distance, we want to use always the AU value. So you can see here the 5 AU, which is our distance from the sun, is plugged in for A. It helps if you write the equation above it if you need to. If you are used to just plug it in right away just like this, that's fine too. We always have a unit with our numbers. And we're going to cube it, so you're going to get that number, and that number is 125. So in other words, 5 times 5 times 5, or 5 raised to the third power. I can go in more detail of how to do that if you struggle with how to use a calculator to do that. And then to get rid of something that's squared, because we just want p by itself, we're going to square root it, because that's the opposite of squaring something. So square root of 125, which depending on what calculator you have, I mean, if you have your phone or if you have a calculator, if you have an actual calculator in class, it would be usually like this. You find the x squared button that you normally square something, and you just hit that second button, and you, because it has a square root above it, you hit the second button, and then the x squared button, and then that will get your square root sign. Or depending on your phone or what calculator you have, will determine that. Or online, look at a scientific calculator online, and maybe that's something that I will pause and find a good one for you to look at. Okay, so when we square root that, we get 11.18 years. So that's how long it takes. If it's 5 AU away, then it's going to take 11.18 years to go around. Okay, so hopefully this is a good summary, a visual and of the 3 laws. Law of ellipses, law of areas, and law of periods, okay? And we're going to focus on that mathematical relationship here. All right. So we saw that. So let's close that. All righty. So we can close this, and you can do the first one on here if you want. It's okay if you don't do it on here. You didn't have to do them on here, because you're going to do these actual same planets right on this assignment here. So, and the graph, you can graph if you want to graph the ones based on just these values, but the graph was already created for you on the interactive, so you don't have to do that either. And then this one's a good review. I might even officially assign that. Maybe I'll just post it on another page if people don't do this, to complete this, to kind of just summarize. Okay? All right, I'm going to go and close that lab now too. Close the key. All right, let's go ahead and pause this. Well, I won't pause it yet. All right, so what does P represent, and what unit will it be measured in? Well, remember, you can look at that key, Kepler's 3rd law, and it says what P represents, what it's measured in, but just to remind you, P is the time it takes to go around the sun, and it is measured in Earth years. A is the distance from the sun, and A is represented with distance from the sun, and its unit is an astronomical unit, or AU. We already talked a little bit about another way to calculate or write P squared and A cubed. P squared is like P times P, or a number times itself. A cubed would be like A times A times A. So that's all that's saying there. So you can fill those in pretty easily, hopefully. I will probably pause and open up my blank document to show work on. So let me put pause here real quick. Okay, so Mercury. So our equation is P squared equals A cubed, which is right here. So you can copy and paste that down if you want every time. And then I would just fill in, I just made kind of a blank setup. I just pretty much copy and pasted this setup to make it a lot easier for you. Copy and paste this exact setup to your document. So that's what I did on this blank screen here. I just copy and pasted it onto a document, but you can copy and paste it right in here. I just didn't want to affect my original. I probably should have made a copy of it as far as student classroom thing ahead of time. I just didn't want to mess with your copy. So that can just be pasted on each one here, and then we're just going to fill in with the numbers, okay? So you can see with Mercury, it says it's 0.39 AU from the sun, which is the number we want to use, but just to give you an estimated amount of how far it actually is away from the sun. That's more of just for you, your reference, and for you to understand how far away it is. 57.9 million kilometers. Okay, so remember a meter stick, a kilometer is 1,000 meter sticks. Okay, so if you have that's very far away, right? And that's the closest to the sun, actually. Okay, so you can see how the distance changes as you go throughout. So that gives you an idea of how far away it is. Okay. Oops, somehow I messed up the setup here. I'll have to fix that. Okay. Somehow it got moved down somehow. All right. So anyway, just copy and paste that right onto your document. I would just take that from the key and copy that over. And so I'm going to show you the example here. So I forgot what the thing was. It's 0.39 AU. So I'm going to take this value. I'm going to just copy it over. I'm going to copy and paste that in here. Okay, so I am always solving for P, and I'm plugging in for A. For physical science, that's what you do. When you get to upper level physics, you will be solving for one or the other. All right, so that's how far away Mercury is from the sun. So we're going to take the number and cube it. So in other words, 0.39 times 0.39 times 0.39. Or on a calculator, you take, I've always typed parentheses, but parentheses 0.39, parentheses raised to. So you'll see like the little caret looking thing, raised to the third power. It kind of looks like, let me type it down here maybe. Raised to the third power. Because the first step is to plug in values. I should say that, plug in / substitute values into equation. I spelled that wrong. Okay, the second step then would be to cube the distance by raising it to that third power. Okay, distance, maybe I should say away from the sun. And this is all to solve for the period or time it takes to go around the sun. Okay, that's what we're trying to solve for. So the first step is to plug in those values, the distance values. Okay, cube the distance away from the sun, which means raise it to the third power. The third, or times it by itself 3 times. The third step then is to have that value written down on right here. Okay, so let me go and do that on my calculator. .059319 is the number that I get. Change that color so you know that's something I plugged in. That's the one I plugged in when I did 0.39 cubed. Okay, so sometimes put that number into the next step for P squared. Cube the distance, which would be that. Take this down here, which is equal to 0.05. Oops, 9319. It made it so a subscript. I kind of messed that up. Undo that. There we go. Equal sign. Sorry about that. So that equaled that value. All right. And the third step is to put that number in the next step. There we go. And I'm finding just write AU once. That's good enough for me to show your work and your units in your work. All right. And then the fourth step is you want to solve for P. So we have this step right here. So to get rid of the P squared, we have to actually square root it. So square root, oops, sorry, I cannot spell, square root the 0. To get the final answer for P. Okay, so we're going to square root that value to get the final answer for P. So the fifth step is to type in, I guess, since we're type in the value for P measured in Earth years. So that's the unit. Okay. All right, so we need to take the square root of, just 1 second. Okay, so I'm going to do that on the calculator here. This is what I get. So I'm just going to round it to 0.24 is fine. Just 2 after decimal is perfect. So the answer would be 0.24. Whoops, my fault. 24. Sure that's what I wrote. Yep. Earth years. So it takes about 0.24, and compared to, remember, the Earth goes around in 1 year. Just gave you that hint. So Mercury goes around in 0.24, equivalent of Earth years. Okay, so that would be your final answer then. Oops, I guess I'll copy and paste. Oops, maybe. Copy and paste that whole thing down here. Okay. All right, so hopefully this helped you on solving for Mercury. And you will go through and solve. So let's review this. To solve for the period, you have this equation is p squared equals a cubed. So you plug in for your distance and you cube it. And then to solve, and you put that number in the next step. To solve for p squared, you have to do the opposite, or so you have to square root it. And then you get your answer for time it takes to go around. So the shortcut that I like to say to kids is you cube it, which means the distance in AU, and then you square root it. Oops, I cannot spell today. It's hard to type in all caps here. So you cube it and square root it pretty much. That's kind of like the hint that I like to tell kids. Cube it and square root it. And that will get your answer for period. Okay, plug it in, put that value in a cube it, and then you square root that value, and that gets your answer. So just show those 3 steps. And again, just copy and paste the basic template from here, and then you're just going to fill in the distance value and then what you got for your values here right onto your sheet. It just makes the easiest thing possible. Just copy and paste. So if I do that, I'm just going to, and it's up to you if you want to copy and paste the equation. Maybe that helps you see how you got that. So you can just hit copy, paste, and then just change the values as you go. Okay. All right, and then just use a regular scientific calculator is fine. Okay. All right, so I'm gonna hit pause here. Okay, so if you I just looked up a calculator, or you can use the calculator on your Chromebook. It probably looks the same way. I'd have to look, but you would type in 0.39, and sometimes you might have the XY button. That's another option, to the 3rd power. So that cubed it, and then we need to square root that, but usually square root has to be typed in first, and then I would type in my number. It just depends on the calculator, like on your phone. I'd have to look to see. It might be opposite. You might be able to type this number and hit square root, and then it'll work. Just have to see what works, and then you get the answer. Okay. Okay, let's look on the calculator here, see how different it is. So let's say we typed in 0.39. Let's see which one it is here. Raised to, I don't know if that's the right one. Yep, it looks like that's the right one. Raised to the 3rd power. Sometimes otherwise it might look like a little caret or like an up arrow. And then let's see if we can just hit square root and it'll get our answer. Yep, it does. So that's how you do that on the your Chromebook calculator. Otherwise, you sometimes on your calculator see raised to the 3rd power. And then square root. In this case, we were able to do it right away. So either way is fine. Okay. All right, so I don't know if there's any questions on the math on this. I went through that example with you. I might go ahead and copy this and make sure this is in maybe a slide or something to show you the example along with your notes. I'll add that on there for you. All right. If you have any questions, let me know. Contact me through Google Classroom. This is something that students usually struggle with. I mean, I just showed you how to use it on your Chromebook calculator. Shouldn't have any problems with that. Every calculator is different. Your phone's different. So you can just like I showed you, do it that way. And it's easiest if you just copy and paste this right into your document and just change the numbers. Hopefully you understand that. Remember, the farther away something is, the longer it's going to take to go around the sun. Or if it's closer to the sun, it's going to take less time to go around the sun. So that direct relationship that you see with Kepler's 3rd law. All right. So I don't know if there's any questions, but let me know through my Gmail, and I'll talk to you guys later. Bye.